In this video, I will explain you what different types of overset meshes and settings are available in STAS-A+, and how you can use them in your simulations. Imagine that you have a part that you want to move or rotate. As long as the body is only moved between different simulations by a set of parameters, it might be possible to simply remesh the flow domain before each simulation. In some simulations it might be possible to rotate the mesh or adjust the boundary conditions instead of actually moving the body. However, there are many simulations in which either of these options is not feasible or prohibitively expensive. In these cases it is better to create several overlapping meshes, from which the final volume mesh is generated on the fly during the simulation. In this example, we are looking at a background mesh which extends throughout the whole flow domain. Our body is a simple block and meshed separately in another automatic mesh operation and assigned to a second region, here called overset region. Both regions can be coupled by creating an overset interface. Before creating the interface, the outer boundaries of the overset region are assigned an overset mesh type, as these are located inside the background mesh. Afterwards, the overset interface can be created by selecting both regions and creating an overset mesh interface via the right-click context menu. As we can see in the properties of the overset interface, the background region was assigned as region 1 and the overset region was assigned as region 0. This is a recommended setting. In most usage scenarios, the meshes are assigned automatically to the correct region based on the set boundary types and the region topology. It is therefore recommended to select the boundary types before creating the overset interface. In some usage scenarios, the automatic detection may fail, and the regions are assigned based on the order in which they were selected when creating the overset interface. With these few clicks, we just created the most basic overset configuration. At the current stage, the overset interfaces are not initialized. The scalar scene visualizing the overset cell type field function has no data to display. It is important to note that when visualizing the overset regions in any kind of scene, we can choose between two representations: overset mesh and volume mesh. The currently activated scalar displayer visualizes a section plane throughout the overset region using the overset mesh representation. The overset mesh representation displays the full overset mesh. Once the overset interface is initialized, the outer cell layer around this region becomes acceptor cells, here visualized in red color with overset cell type 3. The data in the background and overset regions are coupled by interpolating donor cell values to provide data for these acceptor cells. Let's now switch to a scalar displayer visualizing the background region. We can clearly see the donor cells, here visualized in yellow color with overset cell type 1, are in the same location as the acceptor cells in the overset region. The donor cells are surrounded by an intermediate layer of cells, which is used by the hole cutting process. Please note that the cell types 1 and 2 do not necessarily show up in the overset cell type field function and may be included in the set of active cells. The current example uses the layered approach for the hole cutting. This is the default and computationally more efficient algorithm. However, the alternate global hole cutting approach may be more robust when you run the simulation on many cores. Instead of forming a watertight container of cell layers around the overset region, the alternate hole cutting algorithm identifies for each cell centroid of the background region whether or not it lies within the overset region. It is advisable to try both hole cutting algorithms when instabilities occur during the solution process to check whether one of them performs better. Apart from the hole cutting algorithm, the user has several choices for the interpolation option. Distance-weighted interpolation is the easiest and cheapest interpolation option and used as default. Linear interpolation ensures that interpolation elements do not overlap and is therefore especially beneficial in simulations with moving meshes. The user has a choice between 2- or 3-dimensional shape functions. The least squares interpolation is computationally most expensive and ensures an implicit coupling of the equation systems of both meshes through the interpolation function. Next, we will duplicate our geometry to take a look at how to set up several overset meshes at the same time. As all overset meshes are independent of each other, we can simply copy and paste the overset region, translate both regions, and set up the theme. In this example, we need to create 3 overset interfaces between each of the overset regions and the background mesh, as well as an overset interface between both overset regions. The third interface is crucial to allow for the hole cutting between both overlapping overset meshes. Either of the overset regions can be chosen as a background mesh when creating the overset interface. In the current example, there are 6 cell layers between both bodies. The regular overset interface requires at least 4 to 5 cell layers between any bodies or between a body and a boundary. If we move both bodies too close, for example with just 2 cell layers distance, the initialization of the overset meshes will fail, throwing an error message. This issue can be resolved with 2 approaches, either by refining the mesh to increase the number of cell layers between both bodies, or by activating the close proximity feature for the overset interfaces. When the close proximity feature is active, only about 2 cell layers are required between bodies or between a body and a boundary. With this option, cells internally remain longer active, until the cell centroid moved out of the flow domain, and not only until a vertex leaves the domain. If you want to simulate contact between both bodies, you can do so by using the zero-gap overset interface. This interface will deactivate any cell layers between both bodies once there are less than approximately 2 or 4 to 5 cell layers, depending on whether or not the close proximity option is activated. For the visualization of this feature, it is best to switch back to the volume mesh representation. Once the interface is initialized, you can see that the mesh has been deactivated between both bodies and replaced by a wall boundary condition. Imagine that instead of using a background mesh and overset mesh boundaries, we would like to set a wall boundary condition on the outer boundary around our bodies. We can enable the dynamic overset behavior to allow flow between both regions. With this option, the boundary will switch dynamically between a wall boundary and an overset mesh boundary, thus allowing both regions to be coupled. I hope this video gave you a short overview of the different types of overset meshes in StarCCM+ and the related settings. More details can be found in the user manual and the Steve portal.